Hi everybody, welcome to another video in differential equations. Section 1.4 Euler Method. So on this section, we will use numerical method to approximate the solution of a differential equation. In particular, an initial value problem. So initial value problem, what we have is, let's say Euler method for an initial value problem. Initial value problem will be in the form of y, the derivative equal to a function of x and y, and where we have the initial condition of x naught equal to y naught. Right, so that is the problem that we use the Euler method for. So first, the way we do this is, first we have to identify a step size. We know where we start off. The initial value problem, the initial condition. There's a reason we call that initial value problem, because the initial condition, that's where we start. X naught, y naught, which is this point on the graph. That's where we start. That's easy. Right. Where do we go from there? Right. Just like the last problem, we have the direction field, right? So at this point, x naught, y naught, we can compute the slope. And that's where we go. We know the direction. And then to say, let's say we have the slope is this much. How do we know where we start? Right. So with the initial condition, what we will kind of determine beforehand is the steps, a step size, how much we want to go for each step. And usually the smaller the step, the better the approximation. So in this case, let's say a steps is this much. And usually a step size, we call that h. Or some books call delta x. Step size. This is something that we'll establish before we do the problem. And here we use h. Some book use delta x. Right. So we know where we start. That's the initial condition. And then we can calculate the slope. So we go in that direction. And we take the step size. So for that increment, so we stop there. And we say the next point is what we call x1 and y1. Right. With x1, y1, we can calculate the slope. And the slope is in that much. Again, we take the step size of that much of the x values. And so we stop there. And at every new point we have, we can put it back here, we calculate the slope, and we have that direction, and then just chop it up with the same increment of x. And so we have the approximation of the solution. Compared to the actual solution, this may or may not be good, depends on how small the step we choose. The smaller the step we choose, the better approximation. The small step we have, the better approximation. For example, if we want to estimate the function at this values, if we choose a bunch of steps in the middle from there to there, it will be a lot more accurate. Just like when we in calculus 2 or calculus 1, where we use the Riemann sum, use the rectangles to estimate the area under the curve. The more rectangles we have, the better approximation. So just like this, the smaller the step size, the more step size we have, the better approximation. Right. So that visually how Euler method will work. So the Euler method. So for Euler method, we have the initial value problem. And first the first thing we do is establish a step size. So let h be a fixed number. That is the step size. This is something we choose, something small. And so maybe help to easy to calculate. We don't want to choose like 0.12345. That is not very good. Choose something easy and kind of easy to calculate as well. And that is the step size of equally spaced. And after that, we say the solution of the point is approximate as this. So what does that mean? That means the solution is equal to the previous y plus 8 times the slope. Right? So, in a sense, if you can see the approximation or the Taylor series, if we can say, or we start with something very fundamental, the slope. y2 minus y1 over x2 minus x1. Cannot get more fundamental than this. And m is the slope, so let's use y prime instead. Right. And actually we cannot use y1, just use approximation, because m is the slope of the tangent line, but y prime is derivative at the point. It's not, so this is the slope of the secant line, this is the slope of the tangent line, therefore it's not right. So that is y1, right? Right, cross multiply, so y prime x2 minus x1 equal to y2 minus y1. Cross multiply, that's what we have. And move the y1 over, so y2 equal to y prime x2 minus x1, that is the difference between the x's, which is h, plus y1. And so h is the difference of consecutive x, so x2 minus x1, x1 minus x0, and so on. So the difference between consecutive x values is called the step size, or h. So that's what we have. So apparently what we do is just kind of like what we have here. So first we have to know the starting point. With the starting point, calculate the slope at that starting point, and then we set the step about the step size, and then just keep doing that. Mathematically, that's what we arrived here. So when we have x1, y1, we have x2, y2, and then after that, if we have y3, y4, and y5, and so on. So we have different y values corresponding to the equally spaced x values. Right. So how does this actually works? By the way, in this section, I'm going to use different device to do that, because certainly we use a calculator there. So make sure you have the calculator ready, because numerical approximation easier if we have a calculator, right? Now let's look at this initial value problem. We have derivative is equal to x times square root of y, and initial values of y1 is equal to 4, right? Simple enough, right? So, and it will say step size. So, all right, step size we know is 0.1. All right, let's go. Remember, the Euler method is going to be that slope times the step size plus the old y. We keep updating that. Right, so first, Euler method, the first is the initial value problem. So the initial we start with y of 1 equal to 4. So initial condition, we say x naught equal to 1 and y naught equal to 4. That's the initial step. So this is the initial step. So we make a table of n equal to 0, 1, 2, 3, 4, and then those are the x values, these are the y values, and this is the initial condition. That's what we start with. Now, we have x, we have y. Put in here, we certainly can find the slope, right? So we calculate that. So we have x and y, calculate that. Give us 1 times square root of 4, that is 2. Right, so that's good. Right. Next, to calculate the new y values, remember we have that. So y sub n equal to y sub n minus 1 plus h f of xn minus 1 yn minus 1. Pretty much I'm writing this relation here, or we can use that. It doesn't matter. But so we have x and y initial value, we have that, calculate the slope. Next, we take the slope. Multiply the step size and then you go from the previous values. So we start with the previous y values plus step size times derivative. Let me rewrite this so it's more easy to see. So that will be previous values plus h times the derivative. Right, we're going to use that. Right, now we have x, we have y, we can calculate the slope. So this will be 1.1 times square root of 4.2. Let's take 3 decimal places, 2.254. Actually, 4 decimal places. Right, so when we have x and y, we can calculate the slope. Right, one thing we don't need to do any recursively is that we know the increment is 0.1, so we know the next one is 1.2, the next one is 1.3, next one is 1.4. So that's easy to determine. The x values is easy. What we need to update is only the y values. So the y values, we're going to take these y values and we update the y values. So 4.2 plus the step size of 0.1 times the slope. The slope we calculate from the previous step. So we're going to use that. So we have 4.2 plus 0.1 times. If you're using the TID4, you can just go up, highlight that, hit enter. If not, then we have to actually type all of that out. So this is 4.4254. Right. So now we have x and y values. We can calculate the slope. 1.2 square root of 4.4254. Again, highlight that, hit enter, and copy and paste. 2.5244. and we keep going. We're going to update the y value, so we're going to continue from there. 4.4254 plus the slope, plus the step size, sorry, times the step size times the slope. So we can use that value is 4.4254 plus 0.1 times the slope .6778. And then with the x and the y values, you can calculate the slope, and then we have the own values plus 0.1 times the slope, and we just keep doing this recursively, and we will generate the table of x and y values. So those are the solution. When x equal to that, y approximately equal to that, and then we just keep doing that to generate the rest of the table. So that's nice and all. However, if we have the TI-84 here, we actually can just program it to do it automatically. That would be even better. Right, now, a few things about this calculator. If we hit second and the number from 1 to 6, we have the list. And the list, of course, is the list we have more than one values. So I take advantage of that, and we have to use the list here. Right. So this is how we program. So if we use the calculator, initially we let the step size equal to 0.1. That's what we have. Easy enough. X naught equal to 1, y naught equal to 4. Easy enough. And then we update the x values and then update the y values. Right? So that's what we use the calculator. Right. So what I actually translate that into mathematical terms, and then the language the calculator understand is we're going to let some numbers store into H. So we have 0.1, hit the store key, the STO key here, alpha, and that means we let H equal to 0.1. So we store that into a step size. So that's the first thing we do, step size. And then next, initialize the problem. Instead of use x and y, we use the first component of the list and the second component of the list. So I will say x equal to 1, y equal to 4. And if you want the list, hit second parentheses to have a set or a list of number. And I will store STO into list 1. Now with that, the list 1 will have two components. The first one is for x equal to 1. The second one is for y equal to 4. Simple enough. So we have that step. Right. Next, I will make one change real quick. On this calculator, I will have to, if I enter anything extremely long, it will go over, and then we won't be able to see it like this. We'll see. Right. Next, what we do is we're going to update the x values, update the y values. So again, the list will have two components. I'm sorry. The first component will have x, which is the first component of the list. So that is the old x values. We're going to plus h. So if we do that, the first component of the list is updated by the old component plus h. So when we do this, of course, if we want to, so we say the first component of the list plus h store into the first component of the list. But we're going to do that at the same time. And then the second component of the list so that those are the own values. It's don't write the arrow here, that misleading, just write that. And then this is equivalent to update second component plus h times the function of a1 of 1, a1 of 2, store to a1 of 2. Right, we're not going to write like that, we actually type exactly like this. So we have the y values plus h, right? You see, if I'm write like this, you won't be able to see everything we type. So I would hit mode and I switch to the classic mode, to the classic view. So when we have this is the first step. And then initialize. Alright, now I have to type this again. A1 of 1, which is x, we update by h. So to get to the next x values, we just add the step size. So we have 1, 1.1, 1.2. We just keep adding h, the step size, into it. So the first component, we add h into it. The second component, we plus h, the step size, times the derivative. The derivative is x sub n, which is the first component. So h times a1 of 1 times the square root of a1 of 2, which is y1. Right, I have to go to the classic mode so we can see the whole line, everything we type. So we have h times x of n times y of n. So that's good. We can just close the curly bracket and store back into L1. So when we do that, we calculate the new values for the list one, and then we go back, evaluate, update the x, update the y, calculate, update the x, update the y, just going back and go in cycle. You see. So when we hit enter, we have 1.1 and 4.2, which is good. We don't have to type anything again. Just hit enter one more time. We have 1.2 and 4.4254. Hit enter again. 1.3 and 4.6779, and hit enter again. 1.4 and 4.9590, and of course we can just keep doing that. Right, so that's the idea. Initial value problem, initial condition, that's where we start. Using the slope to go to the next point to update the y values. Once we have the new x, the new y, calculate the slope and use the slope to update the y values. Just keep doing in circle. Right? We can also use Excel to do that. The idea is still the same. Right, so I have Excel here. So first, in this column, let's enter the n values. N 0, 1. Right, let's say, oh, there's more. Right, next. Right, next we have x sub n will be equal to the first one is 1, and then y sub n is equal to 4. Let me do this real quick. Right, so we have n, x sub n, and 1 and 4. So those are the values we know. Right, that initial condition. So these are the values we know. That is the initial condition. Let's highlight this. That initial condition. Those are given. Next, based on this one, we can calculate the slope, which is x sub n times a square root of y sub n. Right, so I will have this, never mind, this shell times this one, square root of that, sorry, sqrt, that is the square root of y. Right, 2. Right, let's, never mind. And then next, the x values we can update. The x value we can update easily. So we just say this equal to the previous x values plus the step side of 0.1. And so we will update the x values first. That's not what I want to do. I have too many programs running, so it's kind of slow. By the way, those are way off. Yeah, sorry. So we just have initial x plus the step size plus the step size plus the step size. So that's what we have. So all the x values should increase at the same amount. Now the interesting, how to calculate, how do we update the y values? So the y values will be equal to the old y values plus the step size of 0.1 times the slope. That equal to 4.2. Right. And then with that, we can compute the new slope. Once we have the new slope, we calculate the new y values. And then here we just highlight the rest of the table. I mean this cell. And then copy the formula down. So those are the values we have. Right, so again, 1 and 4, 1.1, 4.2, 1.2, 4.425, 4, 1.3, 4.6779, 1.4, 4.959. And because we, in Excel, we can just copy the whole table down and we go as far as we want to. So, I said there are different ways to do that, but the method is still the same. We start with the initial condition. We have x and y, calculate the slope, use that to update the new y values. Calculate the slope, update the y values, calculate the slope again, update the y values. Just keep doing that. Right, next let's try to do a few more of this. Use the Euler method to approximate the solution when x equal to 1 at x equal to 1 for the initial values problem. So we have this problem. Using the step size h equal to 0.2. And in this case we find the absolute error compared to the actual solution at x equal to 1. Right, so let's just make a table first. So we don't even, yeah, let's not do table, use a calculator this time then. Right, so what do we have? The first step, initial condition. I'm going to just use a calculator here. Initial condition. Actually, we going to do both. X naught equal to 0, y naught equal to 1. If we just make a table, because we still need to see how this works. So let's draw a table. Right, first we have n, the index, and then x sub n, x sub n, and then y sub n, and then the slope. Y sub n, and then the slope. Luckily, the slope is just equal to the function that will be just y. Y prime is equal to y. Alright. Sub n if we want to. Right. And then so the Euler method, this will be updated. Right. So we start with initial condition. X naught equal to 0, y naught equal to 1. We'll just keep going. 1, 2, 3, 4. Actually, we need one more. 5. Right. Now, when we have x, we have y, we can calculate the slope. The slope it happens to be just the y values, which is good. So with those two, we update that. Next, we can update the x values without doing anything. We can do the x values, update the x values independently. So update by 0.2. So 0 plus 0.2, 0.2 plus 0.2 plus 0.2 plus 0.2 plus 0.2 is 1. Remember, we want the values of the function when x equal to 1. So the answer is going to be in this cell. Right. So, right. So when we have that, the solution is we start from the old y values plus the step size times what we have on the previous one times the slope. The update values is 1.2. Next, the slope is equal to just 1.2, so that's easy. With these values, it is 1.2, and we update from there. From the slope equal to 1.2. Next, y sub n. To update the y value, we start with the old y values. So this values give us this. Oh, sorry, wrong one. So update the old values. update the old values plus slope times the step size 1.2. $1.44. And that just keep updating. 1.44. Right. And then the slope will be 1.44. And we will use that to keep updating. 1.44 plus the step size times the zone slope keep doing that. $1.728. The slope is equal to the same y values. This problem is simple enough. When it's complicated, the slope might not be easy calculated, just the same y values. This happens to be the slope equal to the y values, so that makes it easy. Previous one is not quite. And then so we just have that values plus the step size times the slope equal to, and so pretty much we just have that plus 0.2, and we have 2.0736, and the slope happen to be the same as the y values, so that will be the same. And then one more time, and that new slope, and we have 2.48832. Right, so we have approximately y up 1 equal to that. When x equal to 1, y approximately equal to that. Now let's use a calculator and to confirm our calculation, make sure that is correct. Right. The idea of this section is not that much, but I'm showing you using Excel, using a calculator, because later on we might use the same technique of the step that you're using on the calculator will come in handy later. Alright, let's say how do we write this on the calculator. To make the calculator understand, this is what we will write. Right, first we'll let 0.2 store into the step size, so the step size is equal to 0.2. Next, the initial values is 0 and 1. We will store that into L1. So that's initial condition. Next, we will update the list as follows. The first component of that, which will be x, will be plus be added by h. So that's the first component. So this like x of n plus h. When we store back into L1, we update it. And then the second component, L1 up to, so the second component of the list plus h times the function times the slope, but the slope is happen to be just the y values, so that's times L1 of 2. And we store this into L1. Right. So 0.2 store into H. And then next we have 0 and 1 store into list 1. And now we update the list. First component is update by adding H to it. The second component will be equal to the old component plus the step size. You can just type 0.2 or we can use H. Either way works. Times the slope. The slope happens to be just y, right? So it will be just y is the second component of the list. Close the curly bracket, store into the list. What did we? Sorry, second one. We have to store into a list. Right. 0.02, 1.2, that's good. 0.04, 1.44, that's good. 0.6, 1.728, just keep it N and enter. 0.8, 2.0736, that's good. And then x equal to 1, y equal to 2.48832. So that's good. Right, so yeah. So either we do that by hand on the table or we use a calculator to do the recursion. Right, next. This one we actually need to estimate compared to the solution. What is the absolute error? So in that case we have to find the actual solution. We don't know how to solve that yet. But notice in this equation we have this very special function where the derivative is equal to itself. So what function is that? That will be exponential function, right? So the actual solution is y equal to e to the x, because the derivative will be equal to the function itself. The only function of that kind is e to the x. And also when x equal to 0, e to the 0 power is 1. So this is actually the solution. The actual solution is y equal to e to the x. So the actual solution. So this is just coincidence. We can see that the problem is y equal to e to the x. That's why I choose this problem. So e to the x. Now, estimate the error. So absolute error we know is 2.48832. That is the approximation. So we subtract. The actual solution is e to the x, and the solution will be at x equal to 1. So the actual solution is e to the first power, which is just e, or 2.7, 182a, 182a. Yeah, so the actual solution, e to the first. That. So we will take the approximation minus the actual solution. And if we have absolute values, we don't need to write the negative sign. Right, so this is the approximation. This is the absolute error between the approximation and the actual solution when x equal to 1. Right, that's nice enough, right? Finally, let's do one more example. Use the Euler method to approximate the solution of y up to when we have this initial condition. initial value problem is this. I'm not going to use a table here. We just write everything by hand. So initially, the step size, all right, we know that first. The step size 0.25. Store that into H. Then next, the initial condition 0 and 2. Store into L1. And next we just update the L1. L1 up 1, which means the first component of the list, meaning the x values, will be updated by adding the step size. The second component will be updated by, keep doing that. That plus the step size times the slope. The slope in this case is y e to the x. Y is the second component of the list. And then times e to the power of x, which is the first component of the list. And we store this back into list 1. So this process can be will be done recursively. Right, so that's all we have. And where do we stop? We stop when we have x equal to 2. Right, so let's clear this. 0.25 store into H. The list of 0 and 2 initial condition. Yeah, we can store to L1, L2, doesn't matter, just any list. And now update the list. The first component, which is x, updated by adding H. The second component, which is y. Yeah, when we hit second number 1, that gives us L1. And then add H times y, which is L1 of 2, times e to the x, which is L1 of 1. Don't even need the parentheses here. Yeah. So we have extra parentheses. Again, I recommend to keep the calculator in the classic mode so we can see everything we type. Otherwise, it just go everything in one line and you have to go back and forth to see actually what's on the line. Right. Close the curly bracket, store into L1. Right. Next values x1, y1. Keep it enter. Keep hitting enter until we have x equal to 2. The values at 2 approximately equal to 115.99. Right, so that's not enough. Right, once again, if we have the calculator in the math bring mode, that will be complicated. If you use in TI-83, you can only see the classic mode, so you don't have to worry about it. Classic mode is the way to go for this problem. But if you keep things in math bring, it will be difficult to see it. As you see our type, you will see. As you see, it just go run over on one line and difficult to see the whole syntax of the problem. So highly recommend hit mode and go to the classic mode. When we're done, we can always go back to the math print. Yeah. Mode, go to the right mode. And when we're done, select the mode that you want and hit second mode to go back to the home screen. But other than that, the Euler method to estimate the solution of differential equation. So the Euler method for initial value problem is actually it's not that bad. But I highly recommend that you can do this using the calculator, because that saves us a lot of time. If we do that on the table like this, the problem could be very tedious, especially you carry a bunch of decimal places and you don't want to cut off some decimal places. The calculator, though, it will take 10 decimal places, so that will be a lot better than our rounding errors. This one, the example is easy, we can do it by hand, but when it's more complicated, should use the calculator to program. And so initialize the step size, initial condition, and then update the list one. So pretty much just 3 lines for the calculation. Right, so that's all I want to cover for section 1.4, the Euler method for approximation of initial value problem. Thank you for watching.